Hi, my name is Chris Green, and it's an honor to present our work on sequential selection of candidates with my co-authors Morvarid and Karthik. Our motivation for this paper comes from the Army's current recruiting and retention problems that have been prevalent in the news the past few years. As a result, senior Army leadership has brought talent management to the forefront of the national security conversation. Due to the nature of the profession, experience is essential and lateral entry is not possible in the Army. Hence, the Army must assess talent early, develop officers appropriately, and ensure to retain and promote the correct individuals to be the leaders of the future. Although we use the Army as motivation, I assure you some of the similar problems exist throughout other industries as well. The Army's primary vessel for identifying talent and future promotion remains the performance evaluation. Because bonuses and pay raises are not available based on performance, the evaluations serve as the primary incentive for such. The Army uses a competitive evaluation where the highest rating category, most qualified, MQ, is constrained to 49% of a supervisor's total evaluations performed. As you can see from the diagram, the historical number of MQs in an officer's performance file remains the greatest indicator of promotion potential. Here I show you a stylized example to demonstrate the nature of the sequential selection problem. Suppose a manager must select 2 or 5 candidates based on performance. She knows the overall distribution of performance here in stars, but won't know the actual value until he or she enters her office for evaluation. Once the manager makes a decision about a candidate, she cannot change her mind, and once both selections have been made, the search ends. Fast forward to where the manager has rejected 2 candidates and accepted 1 candidate. The decision before her is to accept candidate number 4 and bypass the opportunity to evaluate candidate number 5, or reject candidate number 4 and take a look at candidate number 5, hoping number 5 is equal to or better than number 4. Through this example, you can see how critical the decision is because it can have large-scale impacts on both the workers and the firm. This led us to a couple of research questions as we consider the problem. What are the determinants of human decision in a sequential selection problem? Second, how does the quality of experiment participants' decisions compare with the optimal strategy? And finally, how does the size of the candidates pool affect the accuracy?
Based on the problem that Chris just described, we have employed a theoretical model, and by characterizing the results for that model, we have developed a set of model-based hypotheses, which I'm going to explain to you next. We consider a manager who has to select a subset M candidates from the N candidates who are sequentially arriving for evaluation. At the time of evaluation, the manager can observe the performance of the candidate, but the manager is not aware of the performance of the candidates who are going to come in the future. The manager's decision variable is binary, whether to select or not select a candidate. And this is a dynamic programming model, very similar to the multiple choice secretary problem, with the objective of maximizing the sum of the performance of selected candidates. By characterizing the results for this model, we present a set of propositions. In interest of time, I'm not going to go over those propositions, but we welcome everyone to take a look at the paper where we have all the details on the proofs and results. Based on those propositions, we have developed a set of model-based hypotheses. We have 3 hypotheses. The first hypothesis is focused on high-performing and low-performing candidates, in a way, extreme-performing candidates. We show that the manager should always select a candidate who is in the best performance category, and the manager should not select a candidate in the worst performance category unless it is necessary to fill up the team. As the second hypothesis is focused on non-extreme performing candidates, we can show that there is an optimal decision rule here when the candidates can select up to half of the when the manager can select up to half of the candidates that he or she is evaluating. The manager should select the non-extreme performing candidate only when the number of accepted candidates up to that point is less than the number of rejected candidates up to that point. By doing so, the manager can maximize the overall performance of the selected teams. Our next hypothesis is about the effect of pool size, where we show that in situations when the size of the pool is larger, the manager can basically select a team with a higher average performance. For instance, if the manager has to select 20 candidates out of 40, compared to situations where the manager had to select 10 out of 20 and then another 10 out of 20, we show that in the first scenario, the average performance of the selected team is going to be higher than in the second scenario. And this plot illustrates that results.
We test these hypotheses through a behavioral experiment that was conducted on an online platform. In this experiment, participants were shown 120 candidates in a sequence, and each of these candidates could belong to one of three performance levels: low, medium, and high. And these candidates who were shown to the participants were divided into three different treatments. In the first treatment, which we refer to as the small pool size, the 120 were divided into six sequences of 20, and from each sequence, participants were asked to select 10. And in the other extreme, in the large pool size, the same 120 were divided into two sequences of 60 each, and participants were asked to select 30. Now, dividing our 120 into these three different treatments allows us to test our hypothesis that pooling should improve decision-making in this context. So to see what happens, we devised a measure called accuracy, which compares the decisions participants make against the conditionally optimal decision in that particular state based on the optimization problem we set up earlier. So what do we find? Surprisingly, we find that also, although theory predicts that their performance of the teams that they select should keep improving with the size of the pool, we find that participants in our experiment actually do best in the smallest pool size treatment, both in terms of the overall performance of the candidates they choose and in terms of the accuracy of the decision making, which makes us wonder why. And to explore this, we basically come up with two different explanations. First, candidates or participants seem to have the most trouble when they are selecting or making selection decisions on candidates who are in the medium type, while they have a much easier time making accurate decisions when candidates are either high performing or low performing. An additional factor that seems to confound our participants is situations in which they find that the remaining slots are too few relative to the number of candidates that they have to evaluate. On top of this, we also consider many different behavioral mechanisms that could possibly explain this outcome in the experiment. We consider probability matching, search fatigue, and limited forward looking. And we find that search fatigue and limited forward looking offer the best explanations and organize our data best of all. Thank you for listening to this presentation and hope you will take the chance to read the full paper. Thanks.